Assalamualaikum and good day everyone. So we now proceed with our week 12 of our lecture, okay, which we will discuss about electromagnetic field. Okay, so this is a new type of field that we as compared to previous field that we learn, because it is the combination of both electric and your magnetic field. Okay, so today is 31st of May 2021. Okay, the recorded time of this is 9:47 a.m. Okay, so in this course information, it is explained that what you expected to be learned is that the migration from time invariant electromagnetic field, which is independent of time, to phenomena involving dynamic or time varying electric and magnetic field. So where we start to have time components. Okay, so discussion on Faradays laws and its application for cases pertaining to static circuit time varying field. Okay, moving circuit static field and moving circuit time varying field. Okay, so you guys can read from the course information that I shared. Okay, what should be expected to learn. Okay, and from the Sadiko books, this Sadiko book, you can turn to page 423. Okay, and I will share the slide later on for you to see as well. Okay, okay, so okay, so just like what I explained just now, this electromagnetic field, where we have both components, okay, which is electric and magnetic field, both exist. Okay, and then what is the new thing also, that we start to have our time components. Okay, so it will be have time component, which is this electromagnetic field is time dependent. So the equations involving, for the example equation of wait, I want to turn the page. Okay, so the equation involve for you to have this E. Okay, for example, for your electric, okay, with time components, you have, for example, you have E naught E with your alpha Z, okay, and cos omega T. Okay, you can see this is actually your time component minus your BZ, okay, and this is your direction. Okay, and because it exists in electromagnetic field, both electric and magnetic, so you have also your friend here, which is H. Okay, then you have E naught, okay, is impedance. Okay, with impedance, then you have cos omega T minus BZ minus this angle, and also in Y. Okay, you see this is X and this is Y. Y is different because, you know, in electromagnetics they are orthogonal from each others. Okay, I think you learn from school. Okay, let's say this is your E, for example, then your magnetic will be, okay, your electric and your magnetic. Okay. If you see from this, from the what we have studied in this electrostatic and our magnetostatic, they are the equation that we studied or we introduced or we learned is regardless of time. Okay, for example, you may find, for example, in equation for electrostatic, you may find equation, I think a lot of them. Okay, I just take for example from the supplementary video. Okay, so this is stationary charges because it doesn't have time, component. Okay, and for example for the magnetostatic, okay, let's say your H, okay, this one is you learn from your infinite line charge, and this one is for the magnetostatic. Let's say we have because in magnetostatic what we learn is current, right? In here electrostatic is about charge, so this one due to infinite surface current, so you have J naught over 2 A N. Okay, so you can see it is time dependent. In this magnetostatic, okay, it is moving charges with constant speed, means there is no acceleration. Okay, it's just a moving charges with constant speed. Okay, what is different in electromagnetic? Okay, we will start to have an accelerations. Okay, means that acceleration means that the speed is changes. Okay, this is what happened in electromagnetics, but in magnetostatic it is a constant speed. Okay, and in electrostatic it is stationary charge. Okay, so one of the sources that we can consider where electromagnetic field can happen, okay, which is in where we have alternating current, AC. Okay, I think AC you learn from in your secondary. Okay, alternating current, when it is happen, when we will generate EM field as the products. Okay, whether okay, so we can have for example the sources, okay, is charges. They say this one is constant speed, but for the EM wave, EM field, electromagnetic field, we will start to have charges move at varying speed. Okay, you see, I record at morning, so you can see the background noise. Okay, that's why like it or not, most of the time I record it night time, but you see means by doing so I'm lack of sleep most of the time. Okay, okay, so never mind about my sleep, we continue. So when we have this, okay, you can see this varying speed. You can see this is the wave. So if you have your J equals to this one we learn in our magnetostatic, if I'm not mistaken, then you have your U. Okay, this one is your changing of speed. Okay, so if you turn to page 4 to 5, okay, 4 to 5, So you will start to learn about this. You can read in detail, okay, what they are explaining to you, okay, for this. Okay, they are mentioning stationary charges as your electrostatic field, steady current as your magnetostatic field. Then when you start to have time varying current, this is where you're going to have your electromagnetic field or wave, okay. So if you can see from the supplementary video, okay, it is from the supplementary video by the EMT education, okay, you may refer to lecture 11, okay, lecture 11, where they have make it into weeks, okay, week 12, okay. So please watch it, okay. I learned from them, okay. So now, without further ado, I will continue again. So in you will okay, in this lecture video of transformer EMF, one of them, the lecturer summarized, right, where we have this Maxwell equations, okay. So because in this we will use the Maxwell equation that we learn from the electrostatic or magnetostatic world. We will learn them as well to our time varying field, which is the EM field, okay. So I just rewrite here, okay, what they write in the summary of what we should be learned last time. Okay, if you have a static field, okay, both for EM, both for electric and magnetic, okay, then you have your electrostatic. This one is electrostatic, right? Electrostatic. And this one is your magnetostatic, okay, electric, magneto. And this one is your time variant or time dependent field, okay, time varying field or time dependent field. So in case for this and then this is actually Maxwell equation, okay. And for point form, so you have this is what you learn, right? This is the first Maxwell equation that you learn. And then you also learn about curl of E, which is 0, okay. And then for the magnetostatic field, you learn about the curl of H is equals to your J. And also you learn about the divergence of B equals to 0, okay. So in what is different in the time variant is two of them, which is here, okay, where you start to have your time element, okay. And here as well, the other two, they are the same for both static field and time varying field. You have the same equation. So for the magnetostatic, what differentiation is that you're going to have also time element, okay. This is differentiation of your d over dt, okay. So this is your displacement. They put in the, this is displacement, current, density, displacement, current, density, and this is your Faraday's law. Okay. So you turn to fetch this one, okay, this Faraday's laws, okay, 4 to 6, okay. So the definitions of Faraday's, okay, we start first. The definition is that Faraday discovered that induced EMF, which is you can refer as VEMF, which measure in volt. Okay, EMF is electromotive force. Okay, or we can simply call it EMF, the same. So, but this one is electromotive force. Okay, electromotive force. Okay, so in induced EMF in any closed circuit, okay, in any closed circuit, it must be closed circuit, is equal to the time, okay, you see, time rate of change of magnetic flux linkage by the circuit. Okay, so see, closed circuit equal to the time rate of change of the magnetic flux. Okay, magnetic flux. So what happened, okay, what also explained here, there is a magnetic flux linkage. Okay, so from the previous lecture, I hope where is it? I need to take my previous lecture. Okay, so in previous lecture of the magnetostatic field, okay, you learned about okay, in the previous of week 11, okay, you learned about the flux linkage. Okay, this is where lambda, your flux linkage is equals to n flux. Okay, so we're going to use this again. Okay, you can see okay, then you have for example, L equals to lambda over I, M flux over I. Okay, but this is what is the flux linkage. Okay, so this one is called Faradays laws. Okay, okay, and if we want to put into equations, okay, if you want to put into equation is VEMF equals to your D negative D lambda, your flux linkage, over dt equals to, you know, your, for example, your lambda is equals to your n flux. Okay, so because n is a constant, you can put outside, then you have D flux over dt. Okay, so this is your VEMF. Okay, so what is negative? Okay, what is negative? It shows that this induced voltage, okay, the induced voltage is opposing direction. Okay, opposing direction with the opposing with the direction of the flux that producing it. Okay. Okay. So what is actually is VMF. Okay. Or in this we go into the section of Faradays laws now. Okay. Okay. So let's say you have a circuit that must be closed. Okay. Circuit that must be closed. Okay. And then you have a current moving. Okay. And this time we need to consider time. Okay. So let's say I, which is changes with time. Okay. And then when you start to have this current, and you will also have your B, am I correct? You have your B based on this. So it is, for example, at this plane you have, okay, and until there is a certain time, okay, certain time or at certain range, you will have this is actually passing through. Okay, your B, because this is your time component, so your corresponding B is also dependent of time. Okay, here also. Okay, and this is your closed circuit. Okay, based on the definition. Okay, so when you have B, when you have this magnetic flux, okay, when you have your B, okay, when you have your B passing through these closed circuits, and this closed circuit, you can imagine it can have numbers of turns. Okay, numbers of turns. Okay, these numbers of turn can be 1, can be 2, can be 3, or and so on. Okay, here, if the question only, if this closed circuit only have 1 turn, then it's good, then this one is 1. Okay, so when we have this B passing through this closed circuit, it will induce an VEMF, which is your electromotive force. Okay, so as you learn this, if it's only one turn, then it can be, for example, it can be VEMF. If it's, let's say, if it's only one, okay, so you will have negative D flux over dt. Okay, so you also learn from your magnetostatics. Okay, your flux is actually what? The close the integration of B dot your ds. Okay, so in here, in electromagnetic field, okay, or in this Faradays laws, okay, in Faradays laws, we will learn about three conditions, okay, which relates with this. Okay, so first is that we can have a transformer EMF, and then we can have a motional EMF, and we can have both combinations, transformer and motional EMF. Okay, we can have both transformer plus motional EMF. This is you can refer as what you want. Okay, it's like a hybrid. Okay, means they are both combination of this. So you may refer for the transformer EMF in page 44 to 8. of your Sadiko books, and motional EMF is 430, and your the hybrid, okay, it is 43, okay, of your Sadiko book. Okay, so without further ado, we go first with our I will just use like what the Sadiko book refer. This is case A, this is case B, and this is case C. Okay, so in the case of A, where is the transformer EMF, we are introduced in based on this figure. Okay, later on we see the figures. Okay, we are introduced to this VEMF, which is equals to closed integral, okay, of your E dl equals to negative, maybe I should put this different color so you can see it very clearly, negative your differentiation of your B over dt time component, and you have your ds. Okay, and you learn from your Stokes theorem, right? Where you learn your Stokes theorem, this dA can be changed with what? Okay, let we see from the Stokes. I want to search for the page so that easy for you guys to refer to what I'm talking about. Okay, Stokes theorem. Okay, I think page 91. Okay, for the Stokes theorem, because the Stokes theorem is we change from the line to the surface. Okay, line to surface. So let's wait for a while. I'm trying to see. No, there is somewhere where we discuss about this Stokes theorem. Okay, but I think you can search. It's not on the page 91. It's somewhere along the pages. They are introduced to you this Stokes theorem for further this detail. Okay, but in Stokes theorem they change this this line. Okay, this line, your dl to your ds. Okay, so in Stokes theorem, okay, you have your closed integral of E dl can be from the line, okay, from the line to your surface integral. This is what is all about for this Stokes theorem. Okay, so you start to change from the line and to the surface. So when we want to include this to our transformer EMF, case A, so you will have another derivation of this VMF. Is you have the curl of E, okay, just like this, dot with your surface. Okay, then you have negative, the same thing is this dB over dt, and you have your ds. Okay, you have your negative. So it's also shown in Sadiko book for the two integral to be equal. okay, to be equal, their integrand must be equal. Okay, their integrand must be equal. So you will know that if you see this is ds, this is also ds. So you can see both of this is surface, okay, surface integral. So this one meaning to say that this and this, okay, I put different color, then means the black line, okay, this part, this term should be equal. So that's why here if you take down, curl of E is equal to negative dB over dt. Okay. So in this transformer EMF, your circuit is stationary. Okay, in your A, in your transformer circuit, stationary. Okay, and you have your B with time varying or time dependent, whatever, means you start to have time components. Okay, then your VEMF, okay, VMF is this. Okay, you see this is your BDS. Okay, and then if you want to consider the numbers of turns, okay, negative N dB over dt of your ds. Okay, so this is number of turn and this is negative. Okay, so when we want to solve, okay, you see there's a terms that you have surface, you have your dB dt, and you have your integral. So make sure this, you see when you have ds and then also for the others, so you need to see the coordinate suitable and whatsoever. Okay, so this is your ds. Okay, means you also need to know your z, y, okay, the suitable parts. Okay, so let we go. Okay, we brush through together the related equations, related example concerning this transformer EMF. Okay, I just do some explanation. Okay, so a stationary conducting loop of width 40 centimeter and height 50 centimeter is situated 5 cm from very long wire carrying current in free space as depicted in figure 9.4. Calculate the induced voltage across a small gap created in the loop if your IT, you see, it start to have time components, equals to 5 cos 2 pi 10 to the power 40 ampere. Okay, so we need to see some points, okay, before to make this to solve it. Okay, of course, this is your VMA. Okay, but you need to see a very long wire carrying current. Okay, very long wire carrying current, just like in electrostatic. Okay, if we have very long, we can use our Gauss law. Okay, so this one, it is very long wire carrying current, so we can use what we can use Ampere circuit law. Okay, we can use Ampere circuit law, and you see this is current, okay, moving upwards with IT, and they are asking the induced voltage across a small gap created in the loop. Okay, this one. Okay, so you see the equation VMF is being introduced, negative dB dt, and then just like what I told you, okay, because this is long wire carrying current T, and it's actually long wire, so we can consider to solve it using Ampere's second law. Okay, Ampere's second law, if you can see here, okay, in your page 302, okay, you have your HDL over equals to I enclosed, and you can read for further. I think you should try already. I'm assuming that you already tried the exercise. Okay, hopefully, if not, please try and understand. Otherwise, electromagnetic is more challenging because it's combined your understanding in electrostatic and magnetic field, and top up with this time component. Okay, so in Ampere's second law, just like in Gauss law in electrostatic, so you have HDL. In Ampere's second law also, you need to have like closed circuits, okay, closed region, okay, and it's described by closed integral of HDL equals to your I enclosed. Okay, so in your Ampere's second law, okay, you are obtaining your H, okay, but once you have your H, you can have your B. Am I correct? Okay, because you see, you are introduced to where's my paper just now? Okay, for this example, okay, you are introduced to okay, for example, for this is what example 9.1. Okay, you are introduced to your IT. Okay, and from Ampere's second law, you learn what just now? H dl equals to I enclosed. Okay, so when you have your I enclosed, you have your dl, you can have your H, right? And H is actually interrelated with your B. Am I correct? Okay, so that's why from this you can have your B. Okay, which is if you try from this equation, okay, H dl I enclosed. Okay, I is your, okay, and then you learn also that because this question is asking wanted for us to solve for VEMF, okay, and you know VEMF is what? It is dB dt over of your ds. Okay, so when you already have your B, you put it inside here, then you have your dB over dt times your ds. And what is your ds here? Okay, okay, you can see this one is in y, this one is in z, and this one is in y. So you need to take a vector normal to it, so it is in your x direction, and this one is dy dz. Okay, dy and dz. So your surface of choose is dy dz, and the normal to this surface is actually your x unit vector. Okay, then you settle for your VEMF, because it is about surface integral, so you will have two types, two integral limits, okay, which is your z and your y. Okay, So what is your Z? Z, you can it is from this here. Okay, it is from 0 to 50. Okay, zero to 50. I just put here centimeter, but later on you need to ensure that it's 50 times 10 to the power of -2. Am I correct? Because it's centi. Then how about your Y? Okay, the Y also the same. Here is from 5 centi. Centi means times -2. Okay, the -2. And here you have what? The 40. Okay, means 40 plus 5. Okay, 40 plus 5. So here should be 45 then. Okay, and then you include your results of your dB dt. Okay, where you have this dB and you integrate it. Okay, and then you introduce your dx, dy, dz over x unit vector. Okay, so remember, because this is about as shown in this example, okay, this is about cos and sine, or means you start to have like trigonometry, right? So this one you need to ensure that integrate cos, you get what? Integrate cos, you get what? Okay, differentiate cos, you get what? Integrate sin, you get what? Differentiate sin, you get what? But I believe they should provide it in anyway. I hope they provide it, because we engineers supposed to use, not supposed to memorize. Okay, so we are done with our with our introduction to its electromagnetic field, and we touched on this Faraday's law, and also we briefly discussed about this transformer EMF. Okay, transformer EMF, electromotive force. Okay, you want to read further, it's page 4 to 8, and we will try to cover the other lecture for motional EMF and transformer EMF, transformer plus motional EMF, which is a hybrid case. Okay, so assalamualaikum warahmatullahi wabarakatuh.